An analogy is a comparison based on similarity, usually using words. Not if you already know it. Like our warm-up. Okay, so cat is to kitten as dog is to puppy. This is an analogy. It's a comparison based on similarity. It can be words or it can be numbers or images. It's not restricted to words. Typically, people think of analogy as words, but that doesn't mean it has to be words. A ratio is a comparison of two quantities using division. So we can write a ratio as a fraction. We can write a ratio as a sentence, essentially, or a phrase. And we can write a ratio with a colon. All of these mean the same thing. 2 to 3. A proportion is an equality of two ratios. It's basically a ratio analogy. Okay, so 1/2 is equal to 2/4. Proportion. They're in proportion. If you put two fractions and you say they're equal to each other, but they're not, then you have a situation where this is not a proportion. Okay, so they actually have to have equivalent values. So it's in, cat is to kitten, dog, puppy. It's an analogy of numbers. Okay. So one way we can test a proportion is to use what's called the cross products theorem. And basically, if A over B is equal to C over D, if that is true, then AD equals BC. So written out the way you've probably seen it in the past, I take A times D and B times C. So giving an example for proportion testing, use the one I used before. 1 times 4, and is that equal to 2 times 2? Well, this is 4, this is 4, they are equal, so yes, this is a proportion. If AD is not equal to BC when you do the cross multiplication, then you are not a proportion. Simplifying ratios, otherwise known as reducing fractions if they are written as a fraction. If I have 3/12, if it's a ratio, I can write it in 3 different ways. Now, the fraction, we're used to reducing that. We know that 3 divides by 3 and 12 divides by 3. Excuse me. And so we get 1/4. If it's written in one of the other 2 ways that a ratio is written, you still do the same process. I look at the 2 numbers and I see if they have any common factors, which in this case is obviously 3 because we just did. And so I divide each of them by 3, and I get 1, 2, 4, 1 to 4. Okay. So if I have some other ones, let's just okay. No matter what format they're in, we look at the 2 numbers, 22 and 56. I know they have a 2 in common, so I'm going to try that, just see if that takes me far enough. Divide by 2, I get 11 over 28. 11 is prime. It doesn't divide by anything, so I'm done. 18 and 36. 36 is actually 2 times 18, but if I didn't remember that, I could look at something bigger and say, oh, these both divide by 9. And if I divided by 9, I'd get 2 to 4, and then I would see that and go, oh, those both divide by 2, and I'd get 1 to 2. So if you think of 18, then you just divide by 18, but if you think of something smaller, you just keep going until you can't divide anymore. And the same here, 15 and 75 both divide by 5. So I get 3 to, what is that, 15. And then those both divide by 3, so it's a 1 to 5 ratio. So any questions on that? Simplifying the ratios, the whole point of doing that, the answer always needs to be in simplest terms, but also if you're working a problem and you simplify the ratio first, bless you, then you're working with smaller numbers. It's much easier to work with 1 and 2 than 18 and 36. So if you simplify first, it makes your math easier. So that's the cross product theorem. First of all, does it work? Well, we already did one example, but let's try another one. Let me pick a number that will actually work, not the one I was about to do. Okay, 3 times 21, 7 times 9, 3 times 21 is 63, 7 times 9 is 63. They are equal, so yes, it works. This is a proportion. We can test some proportions. We can test actually some proportions that may not even seem like they would work. Let's try 32 over 28 and 16. Well, that one's actually really simple. Never mind. Well, let's do one that won't work. And we'll put a little question mark over it to say, is it equal? Well, I don't know. So I'm going to do 5 times 14 and 6 times 10. 6 times 10 is 60. 5 times 14 is 70. They are not equal, so these are not proportionate. If we can use a proportion to solve for x. 2/3 is equal to x over 9. Well, let's make it something a little bit better than 9. Give me a number, any number. Okay. So 2/3 is equal to x over 7. We're going to find x. We're going to use the cross multiplication products, the cross products theorem. I'm going to do 3 times x and 2 times 7. Oops, that's not what I wanted. So 2 times 7 is equal to 3 times x. I'm just going to rewrite that. 3x equals 14. Divide both sides by 3, and x is 14/3. Or if you wanted to put it into decimal format, you would get 4.6 repeating. But it's perfectly fine to leave it as an improper fraction. You don't have to go any further, as long as it's reduced. So if it was 28 over 6, you'd make it 14/3 kind of thing. So now we can solve for x. Sometimes we get a situation where we have x plus 2 over 5 is equal to, say, 6 over 11. Same process. We're going to use the cross products theorem. I'm going to do 5 times 6 and x plus 2 times 11. The difference is now I'm going to have to distribute. So I have 11x plus 22 is equal to 30. I subtract 22 from both sides. 11x is equal to 8. Divide by 11. X is equal to 8 elevenths. Yes, they will turn out to be whole numbers sometimes. It's just I'm making it up off the top of my head, so they're not pretty. Sometimes you have multiple expressions. So I want to give an example. Of how to solve this. It's going to require that you FOIL. So again, using the cross products, I have x plus 2 times x plus 1 is equal to x plus 1 times x plus 1. Do you guys remember FOIL? Does anybody need it? Okay. So what I have is when I have two binomials, I have to do what's called FOIL. So I multiply the first, that's the f. So x times x gives me x squared. And then I multiply the outside, so x times 1 is x. And then I multiply the inside, x times 2 is 2x. And then I multiply the last, 2 times 1 is 2. So FOIL stands for first, outside, outside, inside, and then last. That's the order we multiply in. And then the x plus 2x, those are like terms, so I can combine those. So this is x squared plus 3x plus 2. Want to see another one?
No, I got it. Just want
Okay. Then I'm going to do the same thing on this side. And when I do that, I'll get x squared plus 2x plus 1. And then you're going, oh my gosh, there's squareds in there. I don't want to have to solve that. But there's really beautiful thing is going to happen when I subtract x squared from both sides. They're all going to go away. So I'll have 3x plus 2 is equal to 2x plus 1.
Okay, so I use FOIL when?
When you have two expressions, two binomials, that get multiplied together like this, x plus 2 times x plus 1, or here with the x plus 1 times the x plus 1. Take 2x away from both sides, I'll have x plus 2 is 1. Take 2 away from both sides, and x equals 1. So this one does have more steps as far as you have to do the foiling. But then the x squareds end up going away, and you end up with 3x plus 2 equals 2x plus 1, and it makes it easy. That should be a negative. Easier to solve at that point. Okay, notice before. We haven't really talked about that in geometry, but you guys remember talking about in algebra what they called Arrhenius solutions or extraneous solutions, solutions that don't work? What can we not divide by? 0, right? We cannot divide by 0, so I need to take this answer and I need to check and see what happens if I plug it in. I get negative 1 plus 1, which gives me a denominator of 0. So in this case, even though I did all the work and I solved it, x equals negative 1, I can't have x equals negative 1 because I can't have a denominator equal to 0. So that does, in fact, give me no solution on this one. Does that make sense? So anytime when you get your answer, if you have x's in the denominator, you go back and you check them to make sure it doesn't equal 0, because we can never have a 0 in the denominator. Okay. Other things that we can do with proportions, you can find the values of things that are in proportion to each other. In this case, we're doing angles, but you could use proportions to solve, like, I want to make a dessert. that is in proportion 5 parts chocolate, 3 parts caramel, and 2 parts marshmallows or something, and then you could figure out exactly how much of each to put in. So we want to find 2 complementary angles, and just as a refresher, because we did this in the first half, complementary adds up to 90. And then if you have supplementary, yeah, it adds up to 180. Okay, so we need 2 angles that add up to 90 because they're complementary, and we want them to be in a ratio of 2 to 1. Now what you do is you take this ratio, and whatever these numbers are, add x's to them. 2x to 1x. And then I can turn this into an equation. 2x plus 1x equals 90. So that means 3x equals 90, which means x equals 30. Well, 1x is 30. I want to know what the 2 angles are. 1 and then 2 times x. So my angles are 30 and 60. And the 60 was the 2x, which is 2 times 30. Okay. 3 angles of a triangle. Remember again that triangles add up to 180. What is that? Okay, so triangle also adds to 180, so I have 1x to 2x to 3x. So x plus 2x plus 3x equals 180. That's 6x equals 180. So x equals 30 again. And then I have a 1, so that's a 30. I have 2, so that's 60. And then I have 3, so that's 90. So this triangle would be a 30, 60, 90 triangle, and it would be in that ratio of 1 to 2 to 3. All right, so we're going to talk about similar. We talked about congruent, and I just want to do a reminder. Congruent has a symbol of a squiggle over an equal, and it means the same shape and the same size. Okay. Similar is the same shape but not in the same size. Okay. So basically what you have is proportional shapes. So they're the same shape, but they've been shrunk or enlarged. The symbol for similar is this squiggle right here. And that actually is where the symbol for congruent comes from. Similar and equal. Same shape, same size. Whereas similar is just same shape without being the same size. Okay, to test to see if 2 polygons are similar, their corresponding angles are congruent. So if we have, I guess I didn't take that out. Okay, if I have 2 triangles, my angles will all match. And then the ratios of the length of the corresponding sides are equal. So again, if I have 2 triangles and I want to see if they are similar or not, x over a will be equal to y over b, which will be equal to z over c. So all the ratios will be the same for all the sides. And it's triangle 1 over triangle 2, triangle 1 over triangle 2, triangle 1 over triangle 2. Okay. Just remember to always keep the same shape on top and the same shape on the bottom. It doesn't really matter which. I could have put triangle 2 over triangle 1, and that would be okay. It's just that all of the ones on the top or all of the ones from the bottom have to come from the same shape. Okay. Symbol is this squiggle, which we've already got. I'll delete that in a second. We need to list the vertices in order when we are talking about similar polygons. So if I have triangle ABC and I have triangle DEF and they're similar, I have to say triangle ABC ABC is similar to triangle DEF. And what this means is that A is congruent to D, B is congruent to E, and C is congruent to F. Okay, because if we switch that around, then we lose the proportional parts of the sides. So it's really important that they're in the same order. This example that says if ABCD is similar to EFGH, then the following are true. Wow, it did not. Okay. The ratios of the lengths of the corresponding sides is called the scale factor. Okay, so what I have is I have 6 and 3. These are corresponding sides. AB corresponds to EF. So I can either say 6 over 3, which gives me a 2, and I can say that ABD, or CD, not DC, sorry. Okay, again, I had the 6 over 3. So 6 over 3 is 2. And if I write it this way, I can say ABCD is twice EFGH. Or if I flip it the other way, 3 over 6 is 1/2. And then I can say EFGH is half ABCD. And the scale factor is just the multiple between the two polygons. Okay, so let's look at a problem. We have two similar polygons. I have to find the values of x, y, and z. Now, if I look at this, I can determine which sides match each other. I'm going to switch to a highlighter. And I have, obviously, this flat side matches to this flat side. And then we have the long top flat side. Those match. And I don't mean match in size. I mean they match in that they're corresponding in the same area. And then those two, and finally these two. So then when I figure out the values, I know that 10 and 6 are corresponding, so that can give me my scale factor. So my scale factor is 10 over 6. Okay. Now y and z are angles, and remember angles are congruent. So I don't have to do any solving for those. I just have to figure out which angle is which. And z, let me pick a different color. Z is in the same position as 145. So they have to be equal. So z is equal to 145. And then, y is in the same position as this 90-degree angle. So y is 90 degrees. So those were easy. Those we didn't have to, we just had to figure out which one it went with. But once we figured out the matching, the number's already there. But x and 15. X is not 15 because obviously this polygon is smaller than that polygon. We have a 10 and a 6 that prove that to us. So we need to figure out how big x is. And we can use proportions to figure this out. I have a scale factor of 10 over 6, and I know 15. I don't know x. I just have to make sure that the 10 and 15 are both from the large, and then the 6 and the x are both from the small. cross multiply, I get 10x is equal to 6 times 15. So 10x is equal to 90. Divide by 10, and I get that x is 9. Now I have all three missing parts.